Hello, we have given an example about the distribution of maximum of some random variables. In this video, we will obtain similar result for the distribution of minimum of several random variables. Consider that you have two random variables, x and y, and here is, and then you have w, which is equal to minimum of x and y. So we could find similar expressions for that. So first of all, we found that complementary CDF of w, so sometimes we denote this by fw of w bar, which is complementary CDF. Is equal to this expression, and this is equal to the joint complementary CDF of x and y. So this is equal to f bar of xy of w and w. Now, so you could, and this is so using that you can get this expression. If x and y are independent, so you can write this one in terms of product, and then using the derivative, if the distributions are jointly continuous, you get this one. So these are the expressions that we already had. Now, if you have one example, suppose that you have some identically distributed and independent random variables, and suppose that they are uniformly distributed. So the complementary CDF of that is equal to product of complementary CDF. If these guys are uniform, so that means that the expression you can get. So from here you can get the PDF of minimum. So if you take derivative with respect to that, or if you take logarithm first, derivative, and then multiplied by CDF, you get quickly this expression. I leave this to you as an exercise. This is an important exercise. Now, assume that they are uniform. In that case, uniform between 0 and 1. So in that case, fxk of x is equal to 1 if x is between 0 and 1. And 0 otherwise, and CDF fxk of x is equal to x if x is between 0 and 1, is equal to 1 if x is bigger than 1, and is 0 if x is smaller than 0. Now, you could plug this one in the expression of the previous slide, and then we can quickly get this expression. So this is going to be the distribution of the minimum. So obviously this is for w between 0 and 1, and is equal to 1 for w bigger than 1 and 0 for w smaller than 0. So if you plot these CDF for different values of n. So obviously if you put n equal 1, you get uniform distribution. If you could put n 2, you get this expression, etc. So you get a polynomial. And by increasing n, which is the minimum, your distribution, your CDF is pushed toward this x equals 0. So as n increases, so if n is equal 2, you see that your CDF is pushed toward this one. And n equal, this is n equal 5, is pushed further, and this is n equal 10. For n goes to infinity, your distribution becomes just a unit step. Because minimum of infinite numbers which are between 0 and 1, if they are uniformly distributed, one of them will be close enough to 0, and then you get that. So minimum of independent exponential random variable in this example, if these guys are independent and they have all exponential distributions, so this is their CDF, and their PDF is going to be lambda e to the power of minus lambda x ux. So now you put this one in the expression you had, and the PDF of the minimum is going to be like that. So this is a very important and interesting example, which is used in many applications. And you see that if you get from here the PDF, you'll see that the minimum of exponentially independent distributed independent random variables which all have exponential distribution, the minimum also have exponential distribution, and the parameter lambda is equal to the sum of the lambda i's. So in that case, the minimum of them has also exponential distribution, and the parameter is sum of their parameters. So in this section, we have found the PDF of functions of random variables. We have found the distribution of sum, difference, product, division, arctangent, distance, minimum, maximum of two random variables, and multiple random variables as well. In all cases, we found the CDF of the function of random variables and deduced the PDF. For all circularly symmetrical joint PDFs about the origin, we found that the angle has uniform distribution and the ratio of xy has a Cauchy distribution. This is regardless of the distribution of the distance with the origin. So circular symmetry gives you a Cauchy distribution for the ratio x, y. And then arctangent of y divided by x has a uniform distribution. So this is the first arctangent which covers only between minus pi over 2 to pi. If you use the second arctangent, the distribution of arc tan of, let's say, x and y, this is different. So this is going to have a uniform distribution over minus pi and pi. So we have seen that. If the joint PDF is circularly symmetrical about the origin, the distribution of these is quickly found like that. This is the joint PDF, and this is r times 2 pi. The complementary CDF of the minimum of independent random variables is the product of their complementary CDFs. The minimum of independent exponentially random variables with parameters lambda I is an exponential random variable with the parameter of sum of lambda I. So these are important concepts that we have to keep in mind because they have lots of practical applications.